So hello, good morning to everybody. Microphone is active, and this is the second last or the third last lecture. I have to complete the program with you talking about Stokes theorem and divergence theorem, and then we are done. I recall you that these topics are really fundamental in physics, in particular in the study of the electromagnetic fields and the gravitational fields and so on. So probably we will meet again this topic in physics 2 or perhaps in physics 1. And so here we give a more somewhat abstract and not applied treatment that hopefully you can adapt to the cases you will meet in physics courses. So the first theorem I will introduce is a theorem due to Stokes. And there are various kind of presentation of this theorem. This is a very deep mathematical theorem. My opinion is that if you go to book of mathematics, rigorous book of mathematics, then it is very difficult to understand with our mathematical basis. And I will not give you a rigorous proof. I will give you a sort of argument for understanding what happens. What is the reason why Stokes theorem holds, but my roadmap is the following: the fact that the Stokes theorem generalizes Green's theorem to three-dimensional cases. Okay, this is the main idea I want to convey. Okay, and the starting point is the fact that Green's theorem can be applied also to field in three dimensions. Remember that I always insisted on the fact that Green's theorem is for planar fields lying on a plane. But indeed, the important fact is just the circulation we want to compute is on a plane curve. Of course, we can also consider planar fields, but the really important fact is that the circulation is on a plane curve. Okay, so not a helix, for instance, that comes back, but a circle on a plane is good. What I do is just trying to rephrase Green's theorem in a way that brings us to a situation close to Stokes' theorem. So to understand that we can apply Green's theorem also for three-dimensional fields when computing their circulation on a plane curve is just rephrasing the theorem in a language independent of the choice of the coordinates. This is the starting point. So I don't want to do some abstract speech and I go immediately to a picture. We just consider a field F with the three usual components, F1, F2, and 3, and a regular closed curve C, which is this one. And this curve lies in the three-dimensional space. But it is confined to the plane Z equal to 0. So, to all effects, this is just a two-dimensional picture with an additional axis, with an additional vertical axis, okay? That is the Z axis. Now, you can choose your favorite parameterization of the curve C. Whatever parameterization you like, call it R of t. And of course, R of t will have some coordinates, x of t, y of t, and since we are in the plane xy, the third coordinate is equal to 0. Now, we want to compute the scalar product between the field F and the velocity r dot of t of the representative point of the parameterization along the curve. So r dot of t is x dot, y dot, 0. So when performing this scalar product, F3, the third component of F, disappear. Why? Because we have F1 that multiplies the first component of the velocity, F1 x dot. F2 multiplies y dot, which is the second component of the velocity, and then F3 multiplies the third component of the velocity, which is 0. So you see, this is a genuine two-dimensional scalar product because the third component has disappeared. So, for the sake of computing the circulation of F along C, F can be to all effects considered as a planar field, as F1, F2, 0. There are no other components here. And so one can apply Green's theorem. So we have the circulation on the curve C of F. Applying Green's theorem, we have that this is nothing but the double integral on the surface D, which is the interior part of the curve C, of this curious combination of derivative of fields, dx f2 minus dy f1 dx dy. Okay? Now, what is this strange combination? This strange combination is nothing but the third component of the curl of F. So this is very easily done. The third component of the curl of F is this guy. So we can rewrite the third component of the curl of F as curl of F dot n, the unitary vector n. What is n? N is the unitary vector orthogonal to the surface D. And why the third component is equal to the component of n? Because D lies in the xy plane. So one has that the vector n, the unitary vector n, is equal to the unitary vector k. So let us see it directly on the picture. The surface D is here, is inside the curve. So when you consider the orthogonal direction, this is n, it is clear that this orthogonal direction is exactly k. You could object that the points of application on the two vectors are different, but in this kind of reasoning, this has no relevance. Okay, n is the same vector as k, yet it is based on another point, but the vector is the same. This is the idea you have to retain. But notice that there is an ambiguity, a possible ambiguity when you are choosing this n, because n can be chosen upwards or vice versa downwards. But in order to replicate the third component of the curl, so the z component, we have to choose it upwards. Okay, you agree? This is the reason. Here we want to express the third component, so we have to multiply it by k. So we have to choose n parallel to k and not anti-parallel. This is not correct. So let us generalize this choice without referring to the unitary vector k or to the direction of the z-axis. We can think in these terms. So be careful here because this step is extremely important. So we can think in the following way: k here, which is equal to n, is in the direction such that it sees the curve as oriented counterclockwise, or positively if you want, which means that if you imagine yourself to be at the place of the arrow with your head corresponding to the tip and with your foot corresponding to the basis of the arrow, then you look at the curve and you see that the representative point of your parametrization runs through the curve counterclockwise. Okay, this is the important point. And in this sense, there is a coherence between the choice of the normal direction and the orientation of the curve. So this is the idea. The idea is very general. So whenever you have a curve and in a point you want to choose the normal direction of a surface which is bounded by this curve, then the coherent choice, by definition, is that you see, when you are at the place of the arrow, you see the curve oriented counterclockwise. Okay, this is extremely important, and then I'll give you also a rule to not to get confused when doing the choice. It is not so immediate. It is not so easy. Okay. So we go back to our computation. So we wrote down this integral, and this is the comment on the orientation. So I read it again because it is very important. So the unitary vector n on the surface D is oriented in such a way that if one imagines herself or himself at the place of K with a head on the tip, then she sees or he sees the curve C oriented counterclockwise. And here is the other picture. You are here, like the arrow, and you see the parameterization, the point that represents the chosen parameterization of the curve, running through the curve counterclockwise. This is very important. Now, let us go back to the computation. Here is the computation. The circulation, let me write here, on C of the field F, just by the Green's theorem can be written like that, and this can be interpreted, remember our last lecture on fluxes, can be interpreted as the flux of the vector field curl of F. Curl of F is a vector field. If F is a field, the curl is a vector field, because at every point there is a curl, provided that F is regular enough. So this expression is exactly what we called the flux of the field curl of F through the surface D. So in this way, we are able to express the circulation of a field as a flux of another field through a surface. And this is the idea that will lead us to Stokes' theorem. Okay, this nota bene I already said, F is a regular vector field on a space domain omega. Regular means that you can differentiate it with continuity. Then also the curl of F is a vector field on omega. And so we are allowed to talk about its flux to a surface. Okay, and this is the content of Stokes' theorem. But what does Stokes' theorem do? It is able to get us rid of the constraint of having planar curves. Stokes' theorem generalizes Green's theorem to arbitrary closed curves. So, and this is the statement of Stokes' theorem. Let F be a C1 field, so differentiable, and all derivatives of all components are continuous, defined on an open region that we call omega, subset of R3. We are no longer in the plane, we are in R3. Now let C be a regular closed, I forgot here when I wrote it to write closed, but closed is extremely important. A closed curve contained in omega. Then the circulation of the field F on C is equal to the flux of the curl of F on a surface sigma. But what is the surface sigma? Because if the curve is planar, okay, then you can define the surface sigma as the surface internal to the curve, on the plane of the curve. But here we are in the space, the curve is not planar, so what is sigma? And here is the striking answer. Sigma is any surface, an arbitrary surface, which is regular, and such that C is the boundary of sigma. You can choose it at your will, your favorite surface. This is stunning somewhat. Moreover, sigma is oriented in such a way that at every point of sigma, the normal vector, C is C, as oriented counterclockwise. Okay, and here one has to understand a bit, so let me give you this sort of example. So here you have your starting point, which is the curve C. And you want to compute the circulation of the field F along the curve C. Okay? Stokes' theorem tells that the circulation is equal to the flux not of F, but of the curl of F along, for instance, this surface. This is a sort of umbrella whose contour is not a circle, but it is this C, sort of irregular umbrella. So you can compute the flux of curl of F through this surface. But now be careful in choosing the correct direction for the normal vector. The normal vector at every point must be chosen in such a way when you are at the place of the normal vector, you see the curve as running counterclockwise according to the parameterization you gave. And then the surface sigma can be whatever you want. For instance, instead of sigma, we can use this sigma prime here, which lies below. And again, when you are at the place of the normal vector, you have to choose the correct direction, and the correct direction is, again, upwards. So there is a simple rule in order to understand what is the correct direction. This is called the rule of the right hand. That says, take your right hand. It is extremely important that it is your right hand, not your left hand. And put your right hand like that. Okay, like saying okay in the old style American way of saying okay. So you put your thumb up and the other fingers as the first. Now, the thumb represents the normal vector on the surface. So it's like being U, here is the tip and here is the basis. And the other fingers give you the positive, the correct orientation of the curve. Okay, do you agree? And so when you are and then you have just to move it rigidly and adapt to your situation. So when you are not able to immediately see what is the correct normal direction, use the rule of the right hand. Okay, it is very easy, it works, and it applies in many contexts of physics, especially in electromagnetism and so on. You already know some rule of the right hand for computing cross product. This is another one. And this time you don't have to use the pointer and the middle finger in a special way. All the fingers here just mimic the circuit, and the thumb mimics the normal vector. This is the circuit and this is the normal vector. You see that it is correct. Okay, I stop here and then I open another recording for an exercise, for an application of Stokes' theorem.